Hallo liebe Teilnehmer, herzlich willkommen zur ersten Keynote der OOP dieses Jahr. Let's switch over to English now because I would like to introduce you to James Reinders. Hello James. James is an engineer at Intel and also author, co-author and editor of 10 technical books related to parallel computing. His parallel computing experience spans 4 decades, and he is currently focused on helping enable parallel programming in a heterogeneous world. James' keynote is about open approaches for programming heterogeneous computing. Just another quick information for the attendees. If you have any questions regarding the keynote, please go on the website slido.com and use the hashtag OOPdigital. We will then fade in the questions at the end of the presentation and try to answer as many as possible. And I think James and I are grateful when the questions are asked directly in English. James, welcome to OP Conference. We are all happy to have you here. Unfortunately, not in person, but digitally. But that's how it is. So the stage is yours.
Thank you very much. I'm very pleased to be here today. I'm going to talk a bit about heterogeneous computing, which is the future of computing. I'm both a hardware and a software engineer at Intel, and I'm going to start off by talking about some of the hardware motivations, just to give a perspective on how much diversity heterogeneous computing has in store for us and why. That helps set up the problem that I want to talk about the need for open solutions for software. So, the first question one can ask is, why do we need to care? I think over the past decade or a little bit more, we've all come to appreciate that parallelism is part of our life in our computing. I'm going to explain it's going to get even more diverse than that with heterogeneous computing as an aspect of what parallelism means. Hennessy and Patterson wrote a wonderful paper. If it was in Communications of ACM a little while ago, back in February of 2019. If you haven't read it, I highly recommend it. It does a good walk through the history of computing and sets up where we are today. They described the era we're entering as a new golden age for computer architecture. Obviously, they're well known for their work in computer architecture, and they see a lot of excitement going forward. And they even described the variety we're going to see as a Cambrian explosion of novel computer architectures. So that's exciting, especially if you're a hardware architect. If you're a software programmer trying to take advantage of this creates a lot of challenges, and excitement might not be the first word that comes to mind. So if I think about it, computing has been going on for many decades, since electronic computers first appeared in the 50s. We've always seen computer systems be very dependent on a central processing unit. How that was implemented and so forth has varied a lot. In the 80s, we started to get worried that one processor wasn't enough, but then clock rates really took off. So it wasn't until around 2006 we really started to need to worry about parallelism as a way to get additional performance in every computer. So I think we all know parallelism is there so that we can get more work done by adding additional workers. Now, why would we go heterogeneous? Why isn't it okay to just have one type of compute engine? Well, I describe it as we still want to get more and more work done, but now we're willing to have different types of workers, different types of computational engines. If you see an office building being constructed, you'll see different specialties come in. You'll see steel workers come in. You'll see carpenters. You'll see electricians and plumbers. We're pretty used to specialization in our ordinary lives, the world around us. But in computers, this is a fairly new trend, at least as broadly as we see it happening now. And it can really all be traced back to our ability to continue to put more and more transistors on a chip, but not necessarily get performance out of them by the traditional method of frequency scaling. So, transistors continue to rise. Every vendor is able to cram more and more transistors. There are a variety of things going on. You'll see devices have chiplets, many chiplets that are hooked together, or different names for those. Now you'll see what we used to call just a single chip, a processor or a GPU. Instead of being one piece of silicon, it can be tens or perhaps 100 or more in devices. So our ability to cram transistors in one spot continues to rise, but our ability to scale performance needs us to take advantage of parallelism instead of clock rates. Now, this is not new news. This happened more than a decade ago. We ran into a variety of challenges in power, memory, frequencies, memory capabilities, and the ability to find parallelism in a single thread, instruction level parallelism. So frequency is flattened, and our need for parallelism expands. Now, in 2006, that was described as a need for multi-core. That was quite a bit of the discussion. But as we've seen time go on, devices, especially GPUs, have shown their ability to go parallel is a very important aspect of computing as well. So the Hennessy and Patterson, going back to some discussions they've had, they've drawn it this way, different eras of computing, and their ultimate answer is we're going to see more and more heterogeneity in computing to address this leveling off on performance if we don't go more and more parallel. So parallelism doesn't need to be homogeneous. By that, I mean, you don't just take one CPU and then 2 and 3 and 4, or one GPU and multiple. Instead, you can have a mix. This is really only limited by our imagination. So you can have SIMD on a processor, you can have GPUs, you can have FPGAs, you can design your own devices using ASIC technology or custom silicon like TPUs, or lots and lots of AI startups are designing their own novel architectures to go after specialty computations. It might be graph computing, for instance, and it remains to be seen which of these will turn out to be powerful enough or how they will evolve to stay around, but there's a lot of diversity headed our way. So, as I said, you could have a machine with one CPU, of course. You could have a machine with multiple CPUs, of course. And you can attach a CPU to a GPU, a CPU to multiple GPUs, a GPU to multiple CPUs. That variety is pretty obvious, but it gets more and more diverse. You can throw in AI chips and FPGA chips, and what a computer may look like that we run our program on is getting increasingly complex. And memory makes it even more complex. And this is something that most programming languages, actually all major programming languages, aren't prepared for. The idea of memory space not being continuous, that any device in our system can have local memory, and it may share it with other devices. And of course, we've seen this already with even just CPU systems. We see NUMA causing where we put computation and memory, even in a CPU system, can affect its performance. Having the memory a little more local will improve performance. Well, as we see more diversity, that's only going to continue. We aren't going to be able to fake in a heterogeneous machine. We aren't going to be able to fake a flat memory space and get top performance. So at some level in the software stack, a little bit of fiddling is going to have to go on to take best advantage of memory. So this is the world we are heading into. And the question is, how do we survive this with software? This is really near and dear to my heart. And the key thing I wanted to stress in this talk is give a perspective about what we're up against so that our software can take advantage of it. We really want to take advantage of diversity in devices and memory and how they connect and use them all in parallel. And we're really, limited only by imagination. I said that before. And so you can imagine there's a lot of people with great imaginations of what they're going to give us for diversity in hardware. So let me talk about oneAPI. And I want to stress oneAPI is a project that I'm working on with multiple companies. It was kicked off by Intel, really to take a look at what we could do to help create an open ecosystem of tools that help us approach the transition from homogeneous computing to heterogeneous, which is already well underway. And I'm going to talk a bit about what the objectives are and some of the things we've done. But I really want to stress that this is a trend. With or without Intel, I think this is something that has to happen. So I think when we look at our tooling, you should expect that all tooling is going to have to make this transition to survive long term. So here's an easy way that I look at it. When a computer was homogeneous, I didn't really care about the tool chain a lot. Now of course, there were advantages of adopting a tool chain like GCC everywhere or LLVM everywhere. It gave some consistency, but at the end of the day, if I had a C program and I compiled it by a proprietary compiler from a particular vendor, I might get best performance in their hardware, and I could take my same C program, compile it with a different compiler. And that was because my application went through a tool chain and went to a device, and we were done. But when we talk about heterogeneous computing, that one-to-one relationship disappears. My application now goes through some tools and it will run some code on, say, a CPU and a GPU and an FPGA. I just call these XPUs. I don't care what type of processing unit they are. They might be a GPU. One of them might be a GPU from NVIDIA. Another might be an FPGA from AMD or Xilinx, in other words. There might be an AI chip. I don't know when my program is where it's going to run, but I want it to be able to take advantage of these. So really, I need the compiler and the tool chain to help me do that. And because these devices don't come from a single vendor, I have a new problem. And in order to survive this, and I probably don't have a choice, I need to figure out how these tools are going to support me. So when we take a look at the idea we had with oneAPI, you can consider that I've got applications, frameworks, and so forth that try to be pretty agnostic to the hardware they run on. But then I get down to a set of tools, and these are things that implement the languages I'm working in, something to help me with Python, something to help me with C++, like SYCL, different HPC capabilities or AI capabilities. At that point is where my application that's trying to address all of hardware needs to get specific. It needs to start getting down to system level programming and addressing the actual hardware in my machine. So that's where our oneAPI is at, and to go to all of these different processing units. So that's the abstract idea of oneAPI, the concept that there's a critical layer in the software stack that needs to help me make the transition between my programming language, which is trying to take advantage of all hardware, to the point of actually being able to take advantage of that hardware. And so we're very proud at Intel of our work and innovation in all these levels, and we are very committed to open. And I think this heterogeneous computing era really demands a lot more out of this concept of open than we've ever seen before in our industry. So I have 3 tests that I go through mentally thinking about, is something open enough for heterogeneous computing? The first thing is the tools that I use. I want the language, the libraries, whatever I'm using to let me take advantage of any type of compute device, any XPU, if you will. So if I'm doing some coding, I want to be able to dispatch it to a device regardless of vendor, regardless of architecture. Now, there's differences, right? There are differences between an NVIDIA GPU, an AMD GPU, and Intel GPU. There just always are. It's a nature of competition. It's a nature of different designs. I want to be able to take advantage of those differences, but I also want them made common. There's even more differences if I go between a GPU and an FPGA. So nothing's going to magically solve that. It's still something I need to deal with, but I want my tool chain to make it as easy as possible. I realize as a programmer, I have some work to do to span those gaps. But I don't want my tool to artificially say, hey, we don't support that vendor or that type of architecture. So this is really, given rise to things in the past, like the GNU compiler or the LLVM compilers that have really spanned different CPUs. What I'm talking about now is asking that all of the tools start to expand and address the concept of an XPU, being able to create code regardless of architecture, not just regardless of vendor of a single type of architecture. And I want to get performance out of it. So I don't want to hear, hey, my tool supports everybody's GPU, but then find out it makes one of them look really good and the rest bad. I really want to get a consistent level of performance. And again, if you go to open, that helps solve the problem because everyone can participate. It isn't a tool from one vendor. It's an open tool that everybody can participate in. So I want to have the freedom to use any device, but I also want to have the value out of that device. And finally, I need it to be trustworthy. I need to feel confident that if I code to the standard, that it'll last for a long time. And that's really where standards come in. This desire to have a standard defined by the community that will be long lasting, not there to meet the needs of just a few devices, but rather everybody. So this is, to me, I want to see the freedom to use any device, get the value out of the device, and I want to trustworthy. Now, I'm not going to talk a lot about SYCL. I'm going to mention a book we wrote about it. So let me say a few words. So SYCL is a solution for C++ programmers. And it really only does 2 things. One, it gives you some APIs to find out what devices are on a machine in a very open manner. So it may come back at runtime and tell you, hey, I have a GPU from NVIDIA and I also have an FPGA from Intel. Or you may run it and it says, hey, there are no accelerators this time around. So that's a critical first thing to do. And SYCL grew out of the OpenCL standardization effort, but it's higher level and it's very C++. And there have been years of work in the community on this standard. It's a set of class libraries to help, template libraries to help do these 2 things. So one thing is, hey, what devices are there? And the other is connect to a device and give it work to do. And manage the memory and so forth. So it has a set of APIs for that. Now, one thing about SYCL is when you compile it, it's a lot easier if you have a compiler that's SYCL aware because you're producing code for multiple types of devices. And a good SYCL compiler can let you put that all in one source file and then produce a binary for multiple different devices. And that's a little different than a normal flow through LLVM or a GCC. Normally, you're producing a binary for one device. So this is an interesting new capability. But aside from that magic of helping you produce binaries for multiple devices, SYCL is really just a set of template libraries to help you find devices and use them. And so it's really C++ with a class library. And it really emphasizes the openness that gives us the freedom to use any device, get the performance out of it, and have long-term supportability. Now, oneAPI has the same vision, but takes it further than C++. Can we take this to libraries and other languages like Python? Can we do it in our tooling? So let me talk a little bit about that, because this is really, to me, the heart and soul of what we need to do together as software engineers as we embrace heterogeneous computing, is really ask that our tools help us with this. So if I look at oneAPI, it does fit in a particular place in the stack. We've got these devices, and we've got applications that are at a higher level, frameworks and so forth, and we want to connect them. And we really want to take advantage of all sorts of devices. Again, this term that I use, XPUs. Now we have an LLVM compiler project called Data Parallel C++. It is there to implement SYCL in the LLVM compiler stack. And it has backends for Intel CPUs, Intel GPUs, Intel FPGAs. It's got backends for NVIDIA GPUs, AMD GPUs. And there have been some pretty good papers written showing promising results from all of these. Over the next year, you're going to see even more. I think you're going to see more and more adoption. There are a number of companies and labs, research institutions that really want software that they can write that takes advantage of this diversity, but from one language. And so I think SYCL and DPC++ are going to be an important part of that story. And so I'm very excited about it, but it's a piece of it. We have to keep the whole picture in mind. This isn't all just about C++. But if you want to learn more about SYCL, I would encourage you to take a look at our book. I had the privilege of writing this with 5 other authors. We're all at Intel now. I was not when I wrote the book originally. I had taken a break from Intel for a while. But this book is a free PDF download, pretty easy to find. Google my name and Data Parallel C++ book, and you'll find the link to it, and it's here as well. Now, I said it's more than C++. Libraries may be the most important thing. And when I think about heterogeneous computing, I ask the question, hey, if I learn a library like BLAS or matrix, vector, matrix, algebra, it'd really be nice if I could use that interface no matter what device I'm going to. Same thing for video processing or for threading or during neural networks, data analysis, communication. We really need to change our mindset that these APIs need to evolve and be more generous in their ability to talk to connected devices in a heterogeneous world. And we need to rethink that some of these architectures are better than others at some of these computations. Some of these need different data layouts. The memory may be distributed. We need to provide more flexibility in these APIs. But rather than create a different library, a radically different library for every device, I think we really need to think about how do we keep our libraries fairly common. Now, there'll always be some routines that take advantage of special features of hardware, and I don't want to say don't do that, but I really want to apply some energy, some thinking to how common can we make it without giving up performance in a bad way. But how common can we make it so that our code can survive and can take advantage of these devices? Now, this helps everybody. It helps us as software engineers writing our code. If the hardware, if there's a connection to the hardware, it also helps hardware developers. It will come up with a new idea and they can fit underneath these APIs. We already see this with AI. We see that a lot of AI chips work very hard to work under TensorFlow in particular. And if you can prove value under TensorFlow, you're a good AI chip. I just am extending that and saying, when we look at all of our things, including libraries, can we keep extending those libraries instead of breaking them up? Can we have as much common as possible? And you can't make everything common. I'm not saying that, but I've seen amazing work done here in the oneAPI libraries. The vast majority of these are open source. Actually, there's an open source version of all of these. And there's a lot of work going on porting these to different architectures, proving them. And it's exciting times. But this is more than just compilers and libraries. What about our performance tuning tools like vTune? I see no reason that I should have to have a different performance tuning tool for every XPU in my machine. I really ought to expect that my tool can show me what's going on, because when I'm developing my application and I run it on different hardware, I don't really want to have to learn a different tool everywhere. So I'm hoping that every tool out there will take the philosophy of being able to attach and get profiling information from every device. Now, in order to do that, you need to define some APIs that the tools can sit on top of. And oneAPI does that at a certain level, says here are some APIs for profiling. And the more of those that you can support on your device, the more that these tools can just work for you. And I think this is incredibly important, and it extends to debuggers as well. We've helped extend GDB into this universe to do heterogeneous debug so that I don't have to be running one debugger looking at my code on a GPU and a different one for my FPGA. I can do them together. And it's actually extremely exciting being able to step through code that I've written and look at it on different devices. So this is all XPU oriented. So we're really looking at what we can do with open to help hardware regardless of vendor or architecture. So I'm super excited about this trend. And oneAPI is a discussion about what to do. It's very open. It promotes collaboration. Eric Lindell up at Stockholm University gave a talk. These are a couple of slides from a talk he gave, actually probably a couple of years ago now, but he's pretty consistent when he talks about oneAPI. He talks about how open it is. In fact, he said, we pretty much air our dirty laundry in public. There's a lot of discussion about the oneAPI interfaces, SYCL interfaces, SYCL extensions. The debate that's going on with people dedicated to opening up heterogeneous computing is pretty consistent at asking, hey, is this fair? Will it really work on different architectures? Can it really support them well? How do we get rid of the bias for a particular vendor or particular architecture as much as possible, right? We still want to take advantage of unique value that's being offered, but we want it to be open. So the oneAPI specification, which is now at Rev 1.2, I think, came out initially at 1.0 about a year and a half ago after a year-long debate, and it is available to look at. There's been lots of great conversations. There's the minutes from all the different debates are are online for freely to be viewed, what's being discussed, and there's more to come. As we learn more about hardware that's emerging and success people are having using these techniques, we can adjust for the needs of the industry. So truly a very exciting open project. We've seen support for different GPUs. The Fugaku supercomputer is using some elements of this on their ARM supercomputer. We're very excited about all of that because we're learning from each other about how to survive this heterogeneous world. And we're going to increasingly see mixes of devices of all types from different vendors into a single computer. We really need our tools to be open and ready for that. And I may have mentioned, we put a book together. So there are a lot of end users and ISVs, universities, labs, OEMs, framework providers involved in this discussion. And I'm very excited about it. It's definitely something that's piqued a lot of interest and gotten a lot of support. And we're seeing some very exciting results early on. And I expect the next couple of years are going to yield a great deal more evidence that we're heading in the right direction here. So as an industry, we've come a long ways. Our computers used to be very simple. One CPU, we program it to death. But over the last couple of decades, we've been making our computers increasingly complex. But we've only just started. The degree of complexity, diversity of compute power inside a computer is really on the verge of exploding. And we really need open multi-vendor, multi-architecture support in our tooling. And oneAPI is an extremely serious, very important effort to those ends. SYCL is a very important effort, independent effort. We take advantage of it as part of oneAPI. I think we're going to see more and more efforts like this to try to help us survive and thrive in a world of heterogeneous computing. So I really encourage you to take a look at both our book about SYCL to get a perspective. Like I said, it's not super complicated what we're trying to do. You want to start your application, find out what devices there are, query them, and then send work to them. And you can get a perspective on how that is done by flipping through our data parallel C++ book, doing data parallelism in C++. That'll give you a perspective. And then if you expand your mind to include other tools and libraries thinking about it, then you'll understand oneAPI, and you can go look at where is that effort intersecting with your interests and how could you participate and help guide that. Thank you for listening. I know this was, I kept it fairly high level, but if you go Google oneAPI or Google data parallel C++ and SYCL, you'll find that there's a lot of tutorials to dig in on the parts of this that interest you. But hopefully I've left you with a perspective on why open is uniquely important for heterogeneous computing, that we really need openness in our tooling more than we ever have before in order to be able to take advantage of this golden age of computer architecture that we're entering now. And with that, I'd be happy to take a few questions if there are any, to see if I can take this a little further for your interest.
Let's have a look. One question. As oneAPI is developed openly, is Intel working together with ARM, AMD, or NVIDIA?
We are, absolutely. I will say that our interests in open intersect with all of those companies. ARM is very open And the Fugaku supercomputer has taken advantage of this. It's the world's fastest supercomputer, and it's based on ARM processors. They've taken good advantage of oneAPI. So we've had some good discussions about the elements of that support that effort. AMD is involved. AMD is a provider to especially some of the national labs in the United States. And those labs have looked at how they can use oneAPI to help span multiple vendors like NVIDIA, AMD, and Intel. And so there's some good support there. AMD itself, we've had some interesting discussions, and I expect those to be ongoing. And NVIDIA maybe less so, as you might expect. NVIDIA has created a very powerful ecosystem called CUDA, NVIDIA's CUDA. It's proprietary. It's a very strong walled garden that's added a lot of value. So NVIDIA's participation with oneAPI and SYCL is there, but it's not as strong as I think it will be eventually. But you'd have to ask them about where that is headed in the future.
Okay, another quick information for the attendees. Just go on the website slido.com, use the hashtag OOPdigital to ask your questions directly to us, directly to James. I think we can wait a few more moments. Is there anything you want to tell us about the oneAPI thing you didn't tell us in your presentation?
Well, I think for me, all this discussion of heterogeneous computing really comes home when I actually go try it out. So if you are a C or C++ programmer, I strongly encourage you to go look at some of the SYCL tutorials online, or look at our Data Parallel C++ book, which is about SYCL, and go try some of the tutorials. This is something you're going to want as a software professional to get hands-on experience with. And I don't think it matters that much exactly which angle you take on it, but go try it out. It's really exciting to write a program and then run it so that it runs, on an NVIDIA GPU and an AMD GPU, an Intel GPU, an Intel FPGA, maybe, target ARM. The fact that you can get that diversity really gets your head going, and then I think that'll help motivate wanting to dig into oneAPI more and see how you would like to see it evolve.
Okay. I think the attendees saw your contact details, so if there aren't any further questions, feel free to contact James via Twitter, LinkedIn, or his email was also shown. So, James, thank you for your time.
My pleasure. Thank you. Good luck with the conference.
See you soon. Bye.